That last one? All right, good evening. We are going to get started. So I have a bunch of questions that I'd like to do. Some people have some requests on some work that they'd like to see as well. Just FYI, tomorrow, heavy focus on lesson 17, specifically the problems and equilibrium 2. And if there's some bookwork problems, you definitely can ask them, but that's where I'm kind of going. I don't have any like structured work because I know there's enough of the problems that I have assigned you that hopefully those will come up. If you have some of those done, it doesn't hurt to see them again, but that's going to be kind of where we're going to be heading for tomorrow. All right, so on here, we're going to start small, get larger, so I'm going to be just kind of writing the numbers down, letting you know which ones we are doing specifically. I have numerous ones to go through, which I think will give you a really good kind of overview of what's going to be happening for the test on Thursday. So 1 through 3 all ask you to write equilibrium expressions, okay? Now, on a test, right now, later we're going to have a lot more, but right now, these are kind of your options. Okay? So, you have KEQ, KC, and then KP. If nothing else is told to you, EQ means equation. Okay, this means concentration, right? This means pressure. Usually, I'm not saying this is a fact. Usually those are grouped together. If nothing is stated, nothing at all, just says give the equilibrium expression, usually then that's the one that we're doing. You're just usually doing a concentration. Technically, you wouldn't be wrong doing other ones, but a KP deals with gases only, or the ones that can exert pressure, so they don't apply to every single equation because not every equation has gas. Okay, so that being said, just looking at 2C, the reason why I wanted to bring this first one up is that it has something kind of unique in it. It definitely is not a KP if you're looking at 2C, and the reason why is there the states of matter, no gas. Okay, so what I'd like you to do, I'm looking at the right one, yes I am. So we're going to write KC. You could write KEQ as well, but we'll do K sub C. And then, what is it? It's products over reactants, sometimes. Products over reactants. And what is the twist on this one right off the bat?
It's only one. It's a 1 over.
Just
kidding. It's, yeah. Yes, it's 1 over. Right.
Because the products are a solid, right? So I have no products. So my answer, I'll get you started, finish it off. The answer needs to look like that. Let's see if you get it all right, though. Hope you understand that, right? Solids and what don't go in an equilibrium expression? Liquids. Because you can't have a ratio. If you take away some liquid, you just have less liquid. It's pure. There's no ratio. So if you did it right, this is what it should look like. To the third. Some of you, I bet, forgot the third. Hopefully you did. All right. That being said, let's go to one right away, and I'd like you to do this one for me. 3B. So do that one. If you can get this one, you're good. Like you're gonna be fine. I know the font's really small. When you're done, you can look up. Hopefully I wrote that down right. So, I omitted the water because there's a liquid. So please, liquids, we just haven't specifically talked about this for a little while. Liquids and solids do not go into my equilibrium expression. Okay, so let's jump down right away to number 5. So that's just, if you're just asking for the expression, expressions are great, But expressions really are there so then we can utilize that relationship to get to actual answers of equilibrium, amounts, initial amounts. You can do all that stuff utilizing it. So number 5, it says calculate the equilibrium expression K, or constant K at 25 degrees for the reaction. Gives it to you. So here's the reaction. Here's the reaction. It says if the equilibrium concentrations are 0.55, 6.5 times 10 to the negative fifth, and 4.5 times 10 to the negative fifth. So it gives me all concentrations at equilibrium, and I want a K. First off, what K could this be? Or what would this be if I didn't tell you? On the test, I will actually tell you. I would say equilibrium constant, and this just says right now K, but it will say a K sub something. What would this be? It would be Kp, and the reason why is that they're all as ATMs, right? So this would probably be a Kp. So what I actually like you to do first, let's draw out or write the equilibrium generic blank equilibrium expression. So just the expression without numbers, and there might be numbers with subscripts, but not concentrations or pressures. So can you do that properly? Give me the Kp. That's how it would be given on the test. Write out the Kp, the equilibrium expression Kp for the following equation. Can you do it? So as you're finishing that, if you're not done, don't look up. I'm not asking for calculations yet. If you wrote it with brackets, it's wrong. And you can't, there's no argument. Be like, yeah, but I put the compounds and the molecules in the right spots. Unfortunately, it doesn't matter. You have to do it using pressures. Otherwise, it's wrong. And I understand, yes, you got the products over the reactants, you did the right exponents, all that stuff. You got to have the pressures. So if we ask for Kp, make sure, if I ask for it, make sure it's right. So plug them in. Why do I know I can plug them in? Why can I plug these in and I know I don't need to do an icebox? What's the thing that it tells me? Why don't I need to do an icebox? I can just put these in. I have all of them and they are at equilibrium already. If numbers are not at equilibrium, they can't go in an equilibrium expression. It should make sense. This expression is all values go in here equal equilibrium. Otherwise, if you plug them in, what does that equal, by the way? If you put numbers that you don't know if they are or not, you plug them into here, what does that actually equal? It doesn't equal Kp, it equals something else. It equals Q. Because I don't know if it's at equilibrium or not. It might be, but I don't know. So that would equal Q. Good. So let's plug these in if you haven't already. And it's simply by doing parentheses and numbers, nothing fancy. Do not mix them up. That's why I'm slowing down, because I'm not confident here at the moment. What does this favor, products or reactants, without even calculating it? These are at equilibrium. What does this favor? It favors products heavily, because the pressure, right, is much greater on the right than they are on the left. So that's an indication that the reaction favors creating products over the reactants. So always keep that in mind. Obviously, you can always calculate it and find that out, but that's important. Put your sack down, and I don't want to calculate it now.
So it favors the products because there's less moles?
There's more no, I'm looking at the actual numbers. There's more of my products. There's a bigger value here than these. So
Okay.
And also my K is going to be greater than 1. Please understand in the back they gave units. There are no need for units on K values. And if you look at it, it's like ATM inverse or something. Why is that? Because you have 2 ATMs here, right? And you have 3 ATMs in the bottom, so it'd be 1 over ATM. Units, that means every single time it's different. It doesn't matter. And the reason why I tried to prove it to you is that to have units on some, and then if they're exactly equal, there is absolutely no unit. So if something can have no unit, then why try to have units at all? What?
If somebody accidentally puts a unit on the test, it's gonna be wrong.
No, but then it's got to be right.
Say
You know what I mean?
wrong,
What?
it'd be marked wrong then.
No, but it's got to be the right. You got to be right on the unit. So if you are wrong on the unit, then I got to mark it wrong. So how about just let's not do any units on the K for the next month? No units on K. That's basically what you got to do. I know that sounds horrible, and that's really hard for me to say. No units. Oh, okay, I'm not going to finish that sentence. No units. I did it. There we go. All right, here we go. Let's jump down. Number 10. Or over, actually. Sorry. All right, so what you're going to do, it says, given your answer from problem 5. So we just did it. Oh, look at the connection. I have 3 of these. Okay, so you're going to have to look at the equation. What I want, now, only because this is in context of a different problem, I want to see the work, but I want to see it generic first. So I'm going to do one with you right now. I want to show you what I mean, because I might not even give you a number. Can you do this generically? So, it says, given your answer from problem 5, calculate the value for K at 25 degrees for each of the following reactions. First off, they will be at the same temp. Don't get confused. They're at a different temp. That's a whole different ball game, because now that K is different, and you need to know what that is. So, the reason why they say the temp is they're saying it's at the same conditions. They should be the same. So, help me out with the first one, and then I'll let you do the next 2. What has happened to that equation in 10a versus 5? The actual chemical equation. What has happened to it? So there's options. It's been flipped, it's doubled, it's quadrupled, it's cut in half. Like those are things that are, what happened? It's quartered? Uh-oh. Whoa, whoa. It is, that's why I'm doing this first one. Anything else? Or is that it? It's the same direction still, right? Okay. All right, so let's talk about it. If something's cut in half, what do we do to it? Square root, which is also going to the half power, correct? Right? So let's just think about that for a second. If it's quartered, it's going to the 4th power. Would that be? Just like when it's doubled, it goes to the 2nd power. When it's quadrupled, then that means it's going to be to the 4th power, by the way. It's just, that's how it works. So how it would look, first off, we're doing K prime because it's a new K from an old K. So there's 2 ways you can do this. And we're going to write them both down just for you today. It's either to the 4th. Now notice there's no prime there because I'm going to plug this actual number right in there. So what you could do is put your number in, and then with your calculator a caret. And then I would probably think you got to put in parentheses 1/4 or 0.25, caret 0.25. Probably actually the easiest. Or a lot of you have this button. So if you put this in there, but this is how you would write it. So like the actual thing would look like this. Because that's my K, right? I know on my calculator what you have to do is push the button. You have to push the 4, then the X button. It's under math, I believe, for mine. Like if I go to math on my graphing calculator, it's the 5th one down. There's an X to the square root. On Katrina's, it's 2nd and the caret button. So what she'd probably do is put 4 first and then do that. So what I'd like to see is if you can find it on your calculator and get the answer that I have right now. So can you do, I think we can all do this. You can do your number caret 0.25. That would work. Which actually you could punch that in first to see if you have that answer. But then let's see if you get it in another way. So this is actually the answer for this first one. But on the test, I may not even give you a K value in the first place. That's actually the true test. No numbers. What if I just say, hey, this initial one is K, well, how would the expression look? Well, then this is what's more important, is showing how you find it. Now, maybe I'll do both. But I don't know if you can find that or not. But I'm going to see if I can do it quickly. And then when you're done with that, you can quickly do the other 2. So by the way, if you're like, whoa, that's not how I have it written, I have this on my calculator, just FYI. If you round up. It's the same answer. That's what I got at the rounding. So don't freak out. Because I did for about a quarter of a second. I'm like, that's not what I, oh no. So if you can't get it, just, I know I have never really talked about quarters and things, but it's the same concept. It follows along the same exact thing we've done, in case that is a struggle. So what I'd like you to do, quickly find B and C. Why are they double prime, triple prime? Because it's within the same problem, so we don't want to define K's as the same value. So I'm going to pause it if you're home, and you can work on this. What did we do to the second one? Letter B. What happened to it? It's just been flipped, is that it? It's hard. I don't know about you, but I gotta look at it like 2 or 3 times because the stupid NO and NO2, and they both have the same coefficient. It's just enough. So all it's been is flipped. So shouldn't that be it? Right? So then you plug it in, whatever answer that is, you can definitely check it. To me, I'm more worried right now about the expression than anything else. If I ask for, I'll be very clear. Give me the expression or give me the actual value. If I want a value, I'd ask what's in blue over here. Okay. Last one, K triple prime. What did we do to that one? It's flipped and cut in half, isn't it? So, cut in half, it's been divided by 2, so that means it's to the half power or square root. Please be careful. It is not this. It's not that. That's a different value. You'd have a different number. Because then you're taking the square root of the fraction, not just of K. Okay? So I'm going to get rid of that because we don't want to see that. So have a clear understanding, please. Is whatever you're doing to it, if this is still confusing you, just keep it real simple. Whatever you're doing to it, multiplying or dividing that number is actually your exponent now. That's all. So if you're dividing it, it becomes a fraction. Oh, I divided by 2. Okay, that's 1/2. Like I'm dividing it by 2, so now that's my my exponent. If I multiply it by 4, then it's to the 4th power. Doubled it, it's to the 2nd power. So that's that. All right, let's change gears. Let's go to number 14. So let's talk about what has been given here. I hope, when's our test, Thursday? I hope on Friday or the following Monday, depending on if I have them done and if everybody takes it, that I'm not standing up in front of all you saying, you know, I did not see enough started, completed, drawn out ice boxes. We are going to do ice boxes a lot more as we go, but because of the way that the weekends have gone, and although you've been working on your homework, we haven't always been drawing a lot of ice boxes, but it's the way to organize. It's amazing how often students mess things up because you don't organize your numbers. So you don't have to draw it really big. You can draw it in the corner. Like, I may not use this whole thing, but I'm just going to draw this quickly. Like, I can even just do that. Like, I don't need to do a bunch of lines. The ice box is not all my work. My ice box is to organize and to simplify stoichiometry. I will tell you this, though, it's a saving grace. If you have work there, it's the easiest work you'll ever have in AP Chem, because all it is making some columns and writing some numbers and adding and subtracting. And yet, that's stoichiometry. You're doing stoichiometry. It's amazing that all works out. So why I'm saying that is I want to write this stuff out. And maybe if I don't see where these numbers are, this will help. Now, technically, I have all these lines going across. Like, it's going to go like this. Okay, but I just want to make sure I understand what I have. So I'm not acting like I have a secret and I know I don't need to make rows. I might need it. But it says that, first off, K, I'm just going to write this on the side ones. And you already have it all typed there, but I have a K. That's important. If equilibrium concentrations of CH3COOH, which is just acetic acid, is 0.46 moles in 0.5 liters. I love it when it's in 1 liter because I don't have to do any math. So this is at equilibrium. So it's already at equilibrium. So I'm just going to write this by the E. And honestly, I'm going to do this right away. I'm just going to write that below. I'm not going to forget what that is. So what does that actually become? It becomes this. And that of CH3COO minus is, and it tells me that now the wording of that, where do you think that goes? I, C, or E, just based on the wording for the second number. I'm just going to write it right here and then you can slide it up. What does that sound like, just the wording? I or E? What did it sound like? It sounds like E. You're like, well, it doesn't say it's at equilibrium. Yeah, but it didn't tell me anything else, and the first statement was that this one's at equilibrium, and so it's like it's pretty clear. So then this is also at 0.5 liters. So we'll go with that goal, 61.6 times 10 to the negative second. I don't want to mess that up because I would screw everything up. Okay. I'm actually just going to write it as a number instead of an exponent. Or scientific notation. Okay, and then I don't know H. That's the question. So, maybe the icebox wasn't needed on this, but what it did for me is it helped me keep my values in the proper spots. And if I have enough information on my E line, that is awesome, because now I can solve for it. And I have a K, so I can plug all that in right now. So here's my K. And now I'm going to just plug it in. This is the right side. These are my products. So I have 0.0162 times X over 0.92. Would it have mattered if I did not divide it by 0.5 liters? Like, oh, forget it. I'll keep it all in moles and I'm okay. Anybody? Is that okay? How do I know that's not okay? What's the one thing that you could fall back on and be really confident that that's not right? What, Evelyn? Yeah, because and you know what, on the test, I probably, like, these are individual little questions. On the test, I probably would first ask, what is the expression? So you would have to write this out. It's kind of the way they help you. So I try to mirror my questions the same way. So you'd have to write this out. And what am I drawing? Concentration brackets. Moles over liters. So moles work. Moles actually work within an icebox. The problem is they don't work in an equilibrium expression. So to me, get it into molarity and you'll never make a mistake. Now what's frustrating sometimes is then at the end it'll ask you how many moles do you have, and then you got to refigure it out. So what I would do is multiply that, right, and then divide it under. I'll do it with you quickly. 0.8 e negative 5. Anybody else? I got it's small. I don't leave if I keep it as I have it. Anybody else get that? I don't know what it says in the back. I'm going to assume they put in scientific notation. But that's what I got. So, again, right? I multiplied and then I divided that. And I got X. So that's how that one's done. Is the icebox vital? No, but to me it helped organize it. We'll do a couple actual things with iceboxes hopefully tonight. So we'll kind of see that. Okay, so that was 14. And ask questions, please. Where did I get a number? How did I know how to do that? It's a big deal. And today I'm trying to find a little taste of everything for you. So number 19 says derive an expression that relates K to Kp and calculate the value of K at 25 degrees for the reaction given in problem 5. Hey, problem 5 again. So if you go back to problem 5, and I kind of gave you a hint because I didn't actually say what K you found. I probably would not do that. I would just say find the K, because then you would look at this and if you hopefully realize that these are all gases, then hey, that's a Kp. But I do have a Kp, 1.6 times 10 to the 12th. We're going to use that. Now I'm not asking you to derive. It says that on the problem, but you do not have to derive that. This will be given to you. So this is the equation that we have right now. And all I need you to know is you need to recognize if you're doing a KC problem, K sub C, or you're doing a KP problem, and then it asks for the opposite one, and it's not going to go, and by the way, use the equation that you're given. You just need to recognize that you need to convert, and this is how you convert. Okay? So, let's talk about how we do this. Help me out. 1.6 times 10 to the 12th, what was it? Okay, I'm going to plug it in exactly where it was. So that's right here. Here's KC. I just want to do this together. Just the R value. It's always a struggle. I know. You can't pull the trigger on one or the other. I don't know. So here are my two options. Let me write them both at once. And you're going to have them on your orange sheet. Which one is appropriate in this situation? The 8.3 or the 0.08? 0.08. What's the big giveaway? The ATM. It's a gas. It's a gas law. This one, the top one, is when we're dealing with energies, right? Okay? The bottom one is our gas law. So that's the one I need to use. You can't guess, though. You're going to be wrong if you use the wrong one. I'm just writing out the whole unit here. It's not that big of a deal. I'm going to double this up. Temperature, what am I writing? Look at the problem. What? Good. And then, change in N. What is it? Let's go back up. Here's my equation. What's my change in N? -1. And, just so you know, it's only the gases that you can use this with. So if, for some reason, let's say the whole left side was in gas, then it's a 2. Because it'd be 2 minus 0, as an example. Okay? It's always products minus reactants. So, I'm going to write it like that, actually, just so you can see that. It's 2 minus 3. It's not a bad way to write it. I will be very upfront on that. If this problem, by the way, this right here, is always worth 2 points. 1 point for all of the, just using the equation and the answer, believe it or not. The other point is that. I'm not lying. That's how it's done. Are you understanding how to do the moles? That's how they've always broken it down. So it's important. Now, I'm not saying you had to write it like that. You could have done that on the side and then just had a -1. Maybe just getting the -1 is enough. Depends on how they word the final answer. To me, I never believe in coming up with a number from scratch. So we punch that all in. Oh, and by the way, make sure that you're doing this correctly. So it's 0.0821 times 298. Then I do a caret to the negative first. And then I'm going to take 1.6 E12, and then I'm going to divide by my answer. You guys got to start using the answer button if you haven't. You don't start memorizing writing down amounts. I solved for that amount, and now I need to divide by that amount. I can use the whole thing and let my calculator utilize it. And do correct me if I'm wrong, but I got approximately 3.91. Somebody else? Something close. Oh, gosh. Yes, which I wasn't done. Just, sorry. How did I miss that? Some calculators, it's really easy to miss that because it's little. This one's not. That's wrong. Good. No unit? Why? Because K's aren't going to have units for a good month. Here we go. All right. So that's how we would do that. So just if we ever have to convert from one K to another, it's not about memorizing that equation. It never is about memorizing. I know there's some things that we feel like we probably have to memorize, but things like that we do not. All right. All right, let's really start to change it up now. 25. Okay, so the beginning part, this looks like a longer problem than it really is. I just want to start the conversation here. It says reaction of methane with water is given by the following equation. They give you an equation on the side. They say K equals 5.67. Okay? And then it says predict the direction that the system will shift in order to reach equilibrium given the following initial cues. This can and is difficult for many, but I feel the way that we've learned this should not be a major problem. Okay, now you can kind of say shift left or right. You can also say shift towards products or reactants. The thing I do not want to see is something like this. I know I did that today in class. But just an arrow by itself is really not an appropriate answer because, again, that looks like a reaction arrow, and then we're not really actually using words. So shifts left, shifts right, things like that. So I'm going to give you a moment, pause and arrow. Tell me which way it shifts. Your options are always shifts left, shifts right, or no shift. Okay, so If they give you other numbers, so Q equals 11.85, or if it equals this, or if it equals that. So the letter A shifts to the left. Everything you own is on the box to the left. Shifts left. So then letter B would shift right. I'm modeling good behavior by writing it. And the last one would be no shift. Now, please understand, I'm just going to throw this out here, and I know a lot of you are very technical. If I wrote that and you had 3 options, you could add a little word like basically no shift, but don't look into that so much because there might, if it's from like lab data, if it's ever like in the context of a lab, like what is the ultimate, result? And basically you're at equilibrium. Like if you don't have a lot, or your choices are basically not at equilibrium or equilibrium, don't get so technical. You could say basically at equilibrium, or it's roughly at equilibrium if you feel better about adding that extra little adjective, but that would still be a no shift. I know technically it would shift slightly to the right, but you would never be able to measure that with at least how we would be able to do that. So I don't know if we have any questions on that, but I see a number line, and I just place that K, and then I just place the numbers to the side of it, and I know that it has to shift back towards it. And that shift is what it does. It answers my equilibrium shift for me. Okay? So that's, hopefully you can apply that. We'll probably apply that a lot more within ice boxes. And that's the whole point of that one. 33. Keep going through my list. Okay, here we go. So, suggestion. Whenever I'm going to kind of, here, I'll stop talking about it. Let me just write this out. It says hypobromous acid dissociates in water according to the following reaction. Calculate change or concentration of H plus of a solution originally 1.25 molar in HOBr. Okay, so sounds a little confusing how it's worded, but when in doubt and it starts to give you K's, it gives you K, it gives you some amounts, your reaction, your initial instinct needs to go to icebox. We're going to be living in ice boxes for about a month. Cold. So cold. So cold. Okay. All right. So what I do a lot is I just write a little icebox as far to the left or kind of small. It's not what's going to take up all the space. I need to do equilibrium expressions, and I need to do calculations. This is organization, but it is work. So what I'm going to do is I'm just going to make a basic ice box. I just write the ice first. I make my 2 rows. I find the threshold for my products or reactants, and then I separate any other ones. After I've written the equation, don't draw the ice box first. That doesn't make sense. Draw the equation first. Or write the equation first. And now I'm going to place things in here. So away we go. What am I number? 33. So I have, it says originally in the solution. I love it when they give me molarity. It's just one less step I have to do. Now, this is not worded very well. It says calculate the concentration of H+. If it doesn't say anything, again like that, then I'm going to assume that I'm calculating H+ where on here? Where do you think I'm finding it? I, C, or E is what I'm asking, I guess, for H+. What? C, no, never. We're not really ever calculating C. We're going to probably calculate E. This chapter is called equilibrium. So when in doubt, find equilibrium, right? So do I know anything else in this icebox? There's many things I actually know, if you don't feel like it. By the absence of information, that doesn't mean that we don't have information. What else do I know right now that I can fill in? Tyler? On E, I, C, or E? Sounds like you're voting or something. Nay. So then, because of that, that tells me more information. That tells me direction, correct? Every equation, every reaction in equilibrium has to produce what is absent. So this is going to be positive. This is going to be negative. What's nice? They're all ones, right? So my final expression is is that. Final expression, but that's my equilibrium expressions. So that is actually just helping me. Like if I was actually doing a test right now, this is actually what it would look like. Because I'd have this more just up on the side, and I just needed that to get into my problem. So what I'm going to do, just to completely hammer this home, and a lot of times this won't be asked, so you wouldn't have to necessarily write this out, but here is my equilibrium expression. That's where my numbers are going to go, right? Products over reactants, and then I just plug them in. Now, next chapter, this is going to matter. And technically it matters this chapter, but I'm going to be very careful on this. I just want to show you for now. This is 100 times greater. So what that means by that, it's at least. It's more than 100 times. That allows me to do that. You don't have to worry about that right now. But I guess I'll tell you this, is that if RK, it's always just about decimal places. So if it's basically more than 2 decimal places away from each other, you're good. Like, 10, 20, 30, oh, sorry, it's not 10. 10, 100, wow. Rewind. 10, 100, 1,000. If I'm over 3 or more away from each other in the decimal place, then I'm safe. Because when we start canceling things out, I'm going to show you and prove to you is that my final answer, if I cross this out and I have less than 5% difference in my final answer crossing it out and not crossing it out, then I'm okay. But what does crossing things out do for me? It eliminates the quadratic formula, which is a really big deal because I don't want to do it. Not that we can't do it, but that's just more work. That's not necessarily all that needed. Okay? So now, what I'm going to do is I'm going to solve for this, and the whole point is to solve for x. But in this case, let me start showing you an expression you're going to do. Is I want this right here. So if you look at it, in this case, x equals h plus. So instead of writing it twice, why not do it once? Next chapter, this is going to be what we're doing all the time. X equals, and then you're going to write what it already will be, and then the final amount. So if you haven't done it yet, please do so. So this is my math. You might do this totally different. Again, we've learned math portion. It's getting further and further apart from me every year. I multiplied by this, and then what I did is I took the square root. Right? So what it looks like, my actual work here, is I take 1.25 times, maybe I'm telling things you don't need to hear, but I'm going to do it anyway. So I have this right now. Okay? And then I take the square root both sides. And I just leave the answer right on my calculator. And then I hit square root, answer, and correct me if I'm wrong. Anybody else get that? And then if I do that, that's nice, simple, compact. It's all together. Good to go. That's the best way you could label it. I don't know of a better way to do it. I'm not saying you have to do the red work above it. This is, again, not technically a math test, so I'm not saying show me the algebraic steps. But if you need to do it, it doesn't hurt to write it, because if you do make a mistake, it's easier for me to find your mistake. I'll always tell you that. The easier it is for you to show me what you do, the easier it is for me to find out what you did. I hope that makes sense. All right, 39. I know we're getting close to time, but the next one, couple ones will not take as long once you start getting in. So let me just show you this. So it says the equilibrium constant for the reaction blank, or there, is 40. Okay, right there, I'm going to tell you now, this equation, all I'm doing this for tonight is to show you what I mean by 100 times greater, and I want to just set it up. We are not going to finish this one. I already know this is a problem because my k is so big that I'm going to need the quadratic. If a k is larger than 1, starting next chapter, the k is greater than 1, that's a problem. And I can do it. It's just, there's going to be too much error if I erase stuff. If I cancel things out, it's going to have too great of an effect, and my number will be off by too much. But we can still set this up, okay? So I just wanted to show it to you quickly. So it's good to set up an icebox. What I'd like you to do is draw as much of the icebox as possible. Right now, just fill out an icebox. Don't do anything else. Just give me the icebox with as much. Can you fill it all the way out? If it doesn't have actual numbers, then it should have X's. Okay? Do as much as you possibly can. Again, it doesn't have to be big to be effective. K sub C, what do I do here? 0, good. If it's not given to you, you cannot come up to me on the test and hey, Mr. Jesse, you forgot something. Like, no, I didn't. Like, you have to be able to read these problems. Technically, yes, that wasn't said. So you have to make some assumptions. What it's doing is telling you what we have. So whatever we don't have, we don't have. The minute I know that, do I know the direction? Okay, and I don't think I'm going to have a problem like this, but tomorrow I know we do. If I have a number there, how do I figure out direction? This is a good question. What if I have another number there? Make one up, 0.15. How do I know the direction then? What do you have to do? Anybody know? Evelyn? What? It's a good thought, but that's not good. That's a kind of a guessing game still.
Don't you have to solve for Q?
You do, you gotta solve for Q. Remember, every time you ask yourself, which way does it go? If you're like, I don't know which way it goes, I'd have to solve for Q. You'd have all three numbers, you just find out what those equal, and then what does that equal based on K? And then that would tell me if I'm positive or negative. That would be the biggest kind of problem I can give you right now, which I know we have a few. I just went over one with someone today. So, but this is nice because I know it's going in this direction. All right, so I'm just going to write this out for now, just so you can see this, and this is as far as we're going to go. And I might just ask, write out the expression and the relationship of the equilibrium values. I have two things to talk about with this, and then we're going to move on to our last couple problems. One, that is not 100 times greater. And I don't want you to feel like this is unfair, like why are you going through this now? If we're not going to do this, then just let's not talk about it. I am helping you in the long scheme of all of this by seeing the connection that we're doing right now, so you have a very easy bridge to go over when we get into the next chapter. Like, okay, that's the number I'm looking at. This number is smaller than that. I'll tell you now, when you cross, you can't do this. I'm going to do it, but don't. You can't cross out the addition and the subtraction because it's going to have too great of an effect on your final answer. It's going to be too far off. So we would have to do some work. What's one trick that we learned to get away from the quadratic was that if I have two expressions that are the same, I can put them together and take the square root. Doesn't apply here. So unfortunately, this is as far as I can go right now. I know we can do this. I'm going to show you how to do this. And it's not going to come up often because I don't want it to be so heavy on math. But hopefully you get an expression. Last thing I want to point out, that happens a lot with people. This does not automatically now change. This does not do that. because I'm going in this direction, and now you get confused and say, oh, no, these are products and these are reactants, it's going that way. No, because this K is in reference to this relationship that exists here, where these are my products, these are my reactants. That is what that K then refers to. So don't start doing that. It is the context that we have. Okay? So I know I'm running a little bit behind, but I have a lot of quick problems now. So I just want to set one more up. Tomorrow in class we are heavy icebox anyway. All right, some quicker ones. 41, here we go. It says, and there's nothing really to write except the little part on here. It says the following chemical process is already at equilibrium. How would the process respond if the pressure were increased? So this is what I've done. I've increased the pressure. So what needs to happen? What would happen? That's what it's basically saying. And on the back, it's just saying if it's moving to the left or to the right, or to the products or the reactants. So this is a good one. There will be multiple problems like this that you just have to either give me a short one-sentence explanation. That's why on the lab, that's why I did the lab the way I did it. Can you give me a brief explanation or a brief prediction of what's going on? And there was a lot of different things that you had to do besides the volume one. But this one was increase in pressure. So what happens? Which way does this go? Left or right or no shift? Those are your three options. It goes to the right. So what it needs to do, this is me thinking, it needs to lower the pressure, right? To lower pressure, need less gas, right? If they have the exact same amount, unfortunately it's no shift. Like the reaction is incapable of fixing itself. But in this case, I lost it. I have 2 moles of gas on the right, and it's only gas, and 3 moles of gas on the left. So I have 3 moles versus 2, so it's going to shift. And I know I wrote a lot, but it shifts right. And that's what we need to be able to get to. And if I ask for a very brief, short statement, it shifts right to produce less gas, which lowers the pressure. Done. That would be a real nice, real thorough yet short answer. Okay. 42. And all these are kind of short now. The reaction of carbon disulphide with chlorine is as follows. Predict the effect of the following changes to the system on the direction of the equilibrium. And these are really good different kinds of examples in the wording. So let's take a look. A, the pressure on the system is doubled by halving the volume. They bail you out on that. I'm actually not that nice. This is all I would tell you, by the way. So let's do it my way. I would not actually tell you. I think that is weakening the strength of that problem by telling you what happened because they did something to the volume. So if I just tell you that I decreased the volume, now I know obviously you can read the problem yourself and see what it says, but by having the volume, that means in my mind, then I gotta say, oh, pressure went up. Okay, so I'm gonna just say volume is doubled or volume went up or down. So I know unfortunately we just did one that's similar, but this one is different still. So in this case, I need to lower that pressure, so it's going to shift to the right because I have 2 moles of gas on the right and 4 moles of gas on the left. So it shifts right. Letter B. CCl4 is removed. So what's that going to do? It's going to shift to the right because it has to produce more of it. And that's, if you're having a hard time explaining that, just say that. Oh, it shifts to the right to produce more CCl4. Oh, I add CCl4. It's going to shift to the left to consume the excess CCl4. Does that make sense? If it's added, you want to consume the stuff you have too much of. And then lastly, C. Heat is added. So what does that mean? Increase in temp. Try the hardest one of the 3 on here, besides the volume, but we just did that one, so that wasn't as hard. What does this do? Heat is added. You have to, if you're not, you have to make sure, I hope you're using this. What does that do? Where does that put my E? On the right or the left? puts it on the right. So now it's just like letter B or anything else, right? I'm adding or taking away. So I'm adding energy, so it's got to shift to the left in this case. So if you're not understanding what I'm saying, energy was on this side, right? So if I increase it, it's got to shift back to reduce that amount, okay? Just a couple more quick ones here. Let's see if I need that one. Here. Again, I know some of you, depending on your time, but this one's similar. We'll do this together really fast. It says if I triple the volume. So if volume goes up, what happens? What am I thinking? Pressure goes down. So in this case, where does it go? God, all my problems want to do the same thing. I got to increase the pressure again. Oh no, this isn't. Reminder, I said this in class today, at least in one class, the biggest mistake students make is you go from this volume to this pressure and then you go, oh, it decreased pressure. Which way do I go to decrease pressure? I need to increase pressure. That you got to make sure you do that. So which way is it going to go? Goes to the left because there's more moles of gas on the left. What is it? 7 to 3 or something? 7 to 5? So it shifts left. Letter B, the amount of nitrogen is doubled, so in essence, I'm increasing nitrogen, so this is going to shifts to the right. And again, the way I would word that, I would say shifts to the right to consume the excess N2. Right, you want to use it up, that's why it's shifting. And then letter C says heat is added. Let's talk about that one. Heat is added again, so I'm increasing temp. Which way does this one shift? Shifts to the right because my energy is on the right side. So if I increase this, it's got to go to the right. All right. I'm going to just give you some numbers that I would love for you to try, but we aren't going to do them right now. They're multiple choice problems, just to end it today. I'm going to start these tomorrow. So anybody who's watching this or saw this, although anybody who's watching this doesn't have the video or the sheet yet. These are the 5 multiple choice questions that I'm going to quickly do. So if you get a chance to look at them quickly first, then you just have a head start. So it's just a couple more kinds of problems. They're quick and they're fast, but those are the ones that I'd like you to just take a look at. Okay? So a lot of ice boxes tomorrow. Please bring questions and things. You have 4 things technically due on Thursday. If you've been working on it, then you're going to be fine. But you got bookwork, you got Equilibrium 2, which at least 3 people, if not 4, don't even have it, because I have the excess of paperwork up here. Lesson 17, and then the lab. All right. Have a great night.